So here we are at one of the final two review sessions for 4585, where our class today will be led by Reagan.
Okay, so chapter one. What's the difference between like safety and liveness?
Well, okay. I'm just trying to, all right. So I don't have my slides ready in case I want to go to them. So safety means a bad thing must not happen, and liveness means a good thing must happen, right? So theoretically, it would be safe to have 4 red traffic lights in all directions. Because if nobody goes anywhere, then nothing bad can happen. You're safe. So on the other hand, having all 4 greens would give you liveness because you would be able to, you'd have the ability to drive through the intersection, but you would not be safe. So that's the basic distinction. It's a bad thing must not happen versus a good thing must happen. And yes, you can probably engineer questions where it's fuzzy, but I'm going to try not to do that.
Okay, so with mutual exclusion and no deadlock, which one of those would be considered safety?
Okay, well, no deadlock would mean a bad thing must not happen, right? I don't know what the first thing is, mutual exclusion. You're just saying that no 2 threads can access the same data at the same time. Well, that would also be safety, right? Yes. Well, the thing is, a bad thing must not happen. A deadlock is a bad thing, and it must not happen.
The slides do say it's a liveness problem.
Do they really?
I would say it would be a liveness.
Show me. Okay, let me see the slide. All right, because the definition, it seems to me, is crystal. Yeah, it should be safety.
No credit. Progress. But also there's that.
Yeah, I think the idea is that a deadlock, like if you have
Yeah, okay, so I guess
deadlock.
I guess they're interpreting the deadlock as the 4-way red. Sorry.
In my head, I'm thinking like a deadlock is where like all threads are waiting. You can maybe have like a partial deadlock that only some threads are going, but other threads are waiting for something to never happen. So like if a deadlock is a case where all threads are waiting, and like if you consider partial deadlock as a liveness property, then you could also say that all threads waiting being a deadlock is also a liveness.
I would. Okay, so that's what I said. There are places where this gets fuzzy, and I'm proud of you all for remembering this particular slide. It seems to me that a bad thing must not happen. Deadlock is a bad thing. No deadlock. Logically, that fits the definition of safety, but it also, if you want to think about it that way, it depends on what you consider the bad thing, I guess. And in this case, if nothing can do anything, they can't do anything bad.
So waiting not to be a bad thing, but a bad thing would be overriding each other's.
Right. So I guess the caveat here is we want to say that waiting is not being stuck is not a bad thing. And I should have perhaps figured that out from my own analogy, but anyway, it can be fuzzy, as I said.
The CAM protocol, is that basically just a simplified version of semaphores?
A CAN protocol is a simplified version of a single bit. where one thread writes a 1 and the other one writes a 0. But they never, but thread 0 only writes 0 and thread 1 only writes 1, right? It's that kind of thing. That's a can.
Or
Right, but the point is you have two threads writing the bit, but each thread has its own value that it writes and doesn't ever write the other one's value. Whereas a flag is a bit that only one thread writes, and it can write either 1 or 0.
wait, repeat that?
A flag is a bit that only one thread writes to, and it can write either 1 or 0. So in a Peterson lock, we have a flag and a can. We have two flags and a can, right? Flags are literally called flags, but the can is named victim. And you need both a flag and you need both flags and cans to make a Peterson lock.
What's an interrupt?
I'm not going to ask you about interrupts. We haven't really discussed them, but there are ways of handling events in an operating system. But this isn't an operating system course. I know. I'm waiting for the next one. Anybody else can jump in while Reagan's looking for her next question.
Correctness. How do you determine correctness?
Well, I mean, you have to have a notion of what you want your program to do, right? If you want it to produce, and usually that comes with a check of some kind. So if you have correctness for a queue, right, then the first thing in will be the first thing out, right? And the same thing won't come out more than once, and it won't get lost, and stuff like that.
Basically just verifying that it does what it's supposed to.
Right. I mean, you've got some kind of specification. I want a thing that does this, and then correctness is if it does that. And obviously correctness is the most important thing. Because as the joke goes, there's a great optimization if you don't care about correctness.
There's a slide that says that we can solve readers writers without mutual exclusion. How would you do that?
Readers, writers.
Yes.
Which slide is this?
Slide 1 and 2.
Of deck 1?
Yes. The very last thing on the slide says we can solve readers writers.
Oh, it's producer. It should be consumer. 100 what again? 102. Come on. Yeah, okay. So in this concept, readers, writers, is you're imagining you've got a bulletin board and you're reading and writing across the bulletin board. So this is a producer-consumer situation. Now, the producer-consumer code that doesn't require synchronization, I think you're familiar with that one, right? Okay, that's all they're talking about.
One for me, the 3 laws, dollars, goose the funds, and overhead.
You should know them and you should know how they're derived. I probably won't ask you about all of them. I'll just sort of like pick one or maybe two, but you know.
Let's go over how do you derive that part?
Okay. Amdals?
Oh,
All right. Well, let's see. Do you have the slide where I derive Amdals? Oh, here it is. Here we go. Look. Yeah. 104, 105. So let's start with 104. So um speed up equals old execution time over new execution time. This is universal, right? This applies to everything. You should always have that as, if you want to think about it, in a way, that's all the laws. Old execution time over new execution time. Okay. And then the rest is just how you model it. So in the case of Amdahl's law, we have some kind of amount of work we're doing, and we have a fraction of it that's parallel. And so we have an amount of parallel work and an amount of sequential work. And then once you know those things, you can define your speed up. The old time on the top will be just W. On the bottom, you'll have the serial amount of work, which is 1 minus P times W, plus the parallel work, which is P times W, divided by N, where N is the number of processes, right? And now I've got W on the top and then W on every term on the bottom, so the W's cancel out, and I get that. And that's Amdahl's law. It's simple.
math is not my strong suit.
Well, this is very simple math, so that's fortunate. But you see it?
Just fraction part again. Can you go over that part?
Yeah, look, on the top, the total amount of work is the old execution time, right? I've done nothing. It's not sped up by processors at all, it's just running on one core. Now, my new execution time, what I'm going to do is I'm going to take my serial time and leave that alone. And I'm going to add to that, I'm going to add my parallel time, but the parallel time, it's all completely parallelizable, so I can divide it by n, right? And so that's how I construct that fraction. And once I construct that fraction, I can see that the W's cancel, and I have that. I think it's quite intuitive. I mean, if I just throw this equation at you out of the blue, it might not be. But I think once you look at how it's derived, it's fairly intuitive. I don't know what you all think.
Yeah, just had it as the speed up in the bottom, not really in a fraction. They tell how you got from one part to the other. But walking through it, I can see it.
All right.
Stefan starts on the 20.
Okay. So in Gustafson's law, we're going to do something different. Our total work, instead of being a constant like it was with Amdahl's, is it's going to be proportional to the number of processes that we use. So I'm going to have a serial portion of work. At this time, the serial portion is W. And then I'm going to add onto it parallel work, which is K times N. And so the parallel work is K times N, and the serial work is W. And so then I just have to do some algebra, but I do the same thing I did before. So I have W plus K times N, which is the total work in the numerator. And I have W plus K in the denominator because, again, the parallel part of the work gets divided by N. And now I have to just do some algebra. And what I get is that I have 1 plus K times N minus 1 over W plus K, and I'm going to call this K over W plus K. I'm going to call that thing P, a parallel fraction. It's a slightly different parallel definition of parallel fraction than we used before, but it is one that we can use in this problem.
Line 1 speed up to line 2. Where did the extra K come from?
So I added a K. I said W is equal to W plus K, and then K times N is equal to K So all of this is saying is that I added k to this first thing, and I subtracted k from the second thing, right? So k minus k is 0. So plus k minus k is 0. So if I add k to w, I get w plus k. If I subtract k from k times n, I get k times n minus 1. If I subtract k from k times n, I get k times n minus 1. Distributed rule, k times n minus 1 is k times n minus k.
But what's the n minus one come?
I add k to the first term. I subtract k from the second term. That does nothing, right? Okay, so that's how I get to the second line. I added k to the first term. I subtracted k from the second one. I did that because I have a w plus k in the denominator, right? And I wanted a w plus k in the numerator so I could cancel it. This is less intuitive, I'll grant you. But you see what I did? Look, you understand plus k minus k is 0 and it makes no difference? Do you understand that?
Yeah, but I still don't know where the n minus one is coming from.
Okay, k times n, right? Uh, k times n equals k times n minus 1 is equal to k times n minus k, right? Right?
So,
Okay, so look, I start with w plus k times n. All right, so that's going to equal w plus k plus k times n minus k, right?
none once again.
I added k and I subtracted k. Plus k, well, okay, let me do it this way. W plus k times n plus k minus k. How's that? Is that okay? Okay. Now I'm going to just group things differently. Okay. I'm just going to regroup those terms. Okay. How's that? All I did was regroup them, right? Hey,
Hey, sorry for being late. These are not actually involved. It's late.
all right.
Where do you get questions from?
San Diego. Okay, that'll take a whole while to explain.
All I did was regroup them.
Oh, it's review.
Yeah,
This is, Amdahl's.
this is Gustafson's.
I believe you.
I mean, all I did, see, look, I took this term and put them in these parentheses, and this term and put them in these parentheses. That's all I did. Because I want to have a w plus k, because I have a w plus k in the denominator.
Yeah, I think that's.
Okay, and then the next thing is I group this, I say w plus k times n minus 1, right? Right?
Mhm.
Okay. And that's how we get that. All right. And if we have that and we define P as equal to K over, well, then the next line is we just cancel the W plus K over W plus K and we get that.
That's still in the.
Okay. So there are two terms in the numerator. Okay. So if I have A plus B over C, that is equal to A over C plus B over C, right? In this case, right, that A is W plus K, that A and that C are both W plus K. All right? That's all I'm doing is expanding that divide operation. So I get a 1 plus a fraction. Okay, and then I take that K over W plus K and I define that to be P, and I get this term here, this final term, 1 plus P times N minus 1. A practice problem? Okay. I don't know how I would put it. I'd have to make something up. I mean, I could say that you have a Gustafson's law problem that takes, say, 3 seconds on one processor, and it takes 5 seconds on another processor. It takes three seconds on one processor, and it takes 5 seconds on two processors. Um, what is the value of P for Gustafson's? Well, yes, but okay, but so you get what? W is 1 and K is 2, right? So you get 2/3. Right? For one processor, right? So if one processor, your total execution time is 3 seconds, that means W plus K is 3 seconds. And then if you have two processors, W plus K times N is 5 seconds. That means W is 1 and K is 2, right? Okay, look. W plus K times N, okay? If N equal 1, let me put an S there, or T equal W plus K times N. Okay, so N equal 1, T equal 3. N equal 2, T equal 5 seconds. Okay, the solution to that is W equal 1 second, K equal 2 seconds, right? And then P equals K over W plus K, right, is equal to 2/3.
Can you like work it out all the way? Like, how did you get?
Okay, so 2, 1 plus 2, 2/3. I mean, so you can see, right, that the difference between 1 core and 2 core is 2 seconds, right? So that means K is 2, right?
Okay, so you take the difference between.
Yeah. I mean, it's right.
That's something explain how W is 1.
Okay, well, if N equals 1 and T gives me 3 seconds, okay, and K is 2 seconds, then we have something plus 2 equals 3. So that's how I get 1. Are we good?
Thanks.
And there's how Gustafson's law curves look. And then the overhead law. So the idea here is we have an array that we want to parallelize, right? And the amount of work on one processor is normally T1. So that's just the total amount of work to perform the loop in a sequential way. Now, if we want to parallelize that calculation, executing a loop is trivially parallelizable, right? You just divide it into n sections and each processor gets one. However, you add some overhead when you put the mechanisms in there for starting threads up and shutting them down and so forth. And so you add T overhead, right? And so your speed up is, as always, T old over T new, which is T1 plus over, and we're going to define this quantity P to be T1 over T1 plus T overhead. And then our speed up is going to become this, which it requires more algebra than the last. But basically, it's Amdahl's law with a P in front of it, with a P differently defined. But it's the basic idea is always that same thing. It's the same speed up logic.
So just in general, speed up is always just time normal, time over time parallel,
Yeah, time sequential over time parallel.
the fact.
Yeah, it's always you always define it that way. That's the way speed up is defined. Probably.
As my old math teacher would say, you never have to memorize anything, but you have to learn everything.
Yeah, there's in anything that you do, there's a mixture of memorization and understanding how the pieces fit together, right? There's a combination of those things. And sometimes if you just know, you can memorize a small set of things and a couple of rules, and then you can do everything. You could just do everything, right? And if you don't ever understand the rules, sometimes people try to brute force it by by memorizing all permutations, and that's doomed to failure. And anyway, it's like in the physics class, if you always have to memorize the equations, you're not doing it right. But this isn't a physics class, but Amdahl's law is kind of like that. You need to understand the principle. What's that?
Sorry, I interrupted. I was gonna ask like.
Okay.
Chapter 8,
Chapter 8,
monitors.
monitors. It is a class together with its locks and condition variables. It's a complete package of functionality, locks, and condition variables. It's supposed to be an object that is usable by multiple threads. It is not something that watches something else.
So when would you use a monitor over like just a regular lock?
Well, so one of the examples that we give you is a queue, right? And if you want to use a queue in a parallel context, you want a monitor. If you have a thread unsafe queue and you just get a lock every time you use it, that's brittle code that's prone to going bad because you have to always remember to use that same lock with that same queue, right? And then if you get more than one queue, then you have to remember which lock goes with which queue, and you have to code that every time. And that's just awful to look at, hard to maintain, right? The idea is it simplifies. The whole point of programming is to simplify, to tame complexity. And this helps to tame complexity.
Next question, condition variables.
Uh-huh.
What do they do? Like, I know that they have a condition associated with them, but like what happens?
Well, the idea is they have an await and a signal method associated with them. Now, what you do is when you get the lock on something, and you want to do a thing like, okay, so the classical example is we have a queue, and we want to dequeue something from that queue, and so we get the lock and then we look, and the queue is empty, so we can't get a thing from the queue. So what we do is we call our condition variable await method. Now, when we call the await method, we lose the lock and something else gets it. That other thing does whatever it does, and then it calls signal. And when it calls signal, then I wake up and I check, is there now a thing in my queue? Right? When I wake up and I get my lock back, and then I check again, is there a thing in my queue? If there is, then I dequeue it and the method finishes. If there isn't, I go back to sleep and go call await again and go back to sleep. So it's a mechanism by which that you can wait until you can do a task rather than just erroring out. So another option is, right, if I call a dequeue on an empty queue, I could just throw an exception, right? So this is saying, instead of doing that, I'm going to wait until I can dequeue something.
Lost wake up problem.
Right. So the lost wake up problem.
Chapter 8, slide 17.
Okay, so we have a scenario here. So we were talking about the queue, right? And what we're doing in this version of things, is every time we enqueue, we signal not empty. And every time we dequeue, we signal not full, right? And somebody says, hey, I have a brilliant idea. Let's cut down on the overhead. Let's only signal not empty when we transition from 0 to 1. And let's only signal not full when we transition from full to, 1 empty slot, right? So that's our brilliant optimization because, otherwise, in principle, things shouldn't have to be waiting because it's either not full or not empty. However, here's the scenario. Okay, so I've implemented that optimization. And so instead of calling the not empty signal whenever there is a dequeue, a not empty is signaled only when moving from the empty state. And we have multiple processors and multiple and/or consumers. Okay, so here's the actual scenario. Oops. So A and B both try to dequeue an empty queue, and they both wait on the not empty condition, right? C enqueues and signals not empty, waking A. Okay, but then before A or B wake up or do anything, D enqueues, and D does not signal because the queue is not empty, right? And now what happens is A wakes up and dequeues because the signal is only going to wake up one thing. So A dequeues and wait but B does not because B doesn't wake up, right? Because these two things happened before either of these things dequeued, right? Only one of them was able to get an item out of the queue and the other one's still waiting even though there's something in the queue. Now, one solution to that is to signal all instead of to just signal.
Is a good solution for lost wake up?
There's never anything that's always true. It usually works, right? And if you're coding this way and your code isn't working, I guarantee you're going to try making all your signals into signal alls just in the hopes that it will work. But in this particular case, signal all is a good solution.
Okay, what is the use case of reentrant locks?
It's actually the way anybody would want to code, right? I mean, the use case is that you've got a class with a bunch of different methods on it, and you want it to be thread safe. Now, if a lock is not reentrant, and if you already hold the lock and you call the lock method, you will deadlock yourself, right? And having a reentrant lock is just a good safety measure against deadlocking yourself.
Is there any situation other than like a reader's writers where you would not use a semicolon?
I've never wanted to use a semaphore ever. There's nothing wrong with it. I've just never wanted to use one. Usually I either want a lock to prevent a piece of data, or I don't. It's not common for me to want three things to get into the critical section rather than just one. It's just not something I remember ever using. I mean, I can sort of imagine that like you're parceling out database connections or something like that. But I haven't written that code, so I haven't had a need for it myself.
Can you explain composability again?
Yeah, so composability, it comes up in two places. It comes up, and one of the places it comes up is in the context of locking code. And the idea is you want to be able to look at the pieces individually, right? And you don't want to have to understand everything all at once because your brains are not necessarily big enough to understand your whole code base at once, right? I know mine isn't. So composability says that I don't have to understand everything all at once to understand if it's correct. I can just look at the pieces. And if the pieces are correct, then I can be confident that the whole is correct. But with locks, that doesn't apply, right? Because the problem is if you're holding a lock, you may not know that you're doing that. And when you get another lock, that might get you into a deadlock situation. By the way, with the guard example homework, I didn't know if you all saw the Discord. Okay. But every one of you made the same mistake about guards.
Amen.
Yeah, so the notion is when I say run guarded, I don't know what's going on there.
It's gonna be like a notification or
It's
something.
probably gonna be like, hey, go buy this thing.
Oh, well, okay. It was just waiting for me to click something, I guess. So the point is, when I call run guarded, I don't know when the body of that method, that task I'm giving to the guard, I don't know when that's going to execute. It might execute immediately or it might execute some unspecified time in the future. So I have to wait for it, right? I can't just exit and count on it having happened. So when I coded my version of this, right, I return the future that run guarded creates. And then I consume that future when I do my parallel loop, and inside there I do my sequential loop, right? And the sequential loop returns a future, and I give that to the parallel, and then each element of the sequential gets the future from the run guarded. So the future that comes back gets consumed, right? There's no must consume rule in Java, but this is the reason for the must consume rule, so that you don't forget to wait for things. Make sense?
Is there actually an explanation for why the join can only occur in the entry function?
Well, the point is that a join is dangerous because it's blocking. right? And I would prefer to never join at all. And that's why we designed Guardian so that main could return a future void and so that the actual join would be done by the system and you'd never see it. But every time you do a join, you're blocking. And that means a potential for deadlock and a potential for slowing down your thread pools. So you can't get out of doing at least one join in a Java program. So I like to do only one.
Okay.
If you do only one, you should be safe, at least from deadlock and clogging thread pools. You could still fail to wait for things. Termination detection of parallel programs is, you know, there's a fair amount of options and logic and complexity, but I think if you can wait for all the things that you started is a good solution.
Can you explain canonical order again?
Yeah, so canonical order just means some arbitrary order that you never change, right? So one way to order things is by the address in memory where the lock is stored. And you can get that from system.identity hash code in Java, for example. And so long as you always get the locks in the same order when you lock them, you can't deadlock, right? The problem comes when I try to get locks in different orders. If thread 1 tries to get lock A and then B, and thread 2 tries to get lock B and then lock A, you have the possibility that each one succeeds at the first thing and both wait forever for the second thing. But if both threads always try to get A before B, always try to keep those locks in their alphabetical order, then that can't happen. Even if you do other things like thread 1 wants to get A and B, and thread 2 wants to get B and C, no problem. It's getting them in order will prevent the deadlock.
Have we asked any questions about OpenMP yet?
We have not.
That's
Okay.
on my list.
It is on Reagan's list, but go ahead and ask one if you want to.
We'll be a little asynchronous. So as for the slide 6 on the 4585 OpenMP slides, do we have to know all of these? There are a bunch of definitions for the types of constructs that happen in.
Hold on. Let me get to where you are.
Sure.
Slide 6, you say?
Yes. It basically lists a number of definitions.
It's like all of them. Right.
Yeah, no, you don't have to memorize all of that. Um, what should I have you understand?
Like, I don't think I've seen schedule.
Yeah, no, I don't think he probably didn't talk about that. And that's that's a schedule is a way of trying to decide how to chop your loop up into pieces. And it's one of these things that if you're trying to get performance and you want a little false hope, you can play with that.
Also,
Yeah.
that's good enough for me. I'm not gonna study it.
I wouldn't worry about the schedule, but I guess he talked about barrier and critical, right? Um, and parallel for, and shared and private. And right, he talks about those, right?
Is OMP four the same as marching four and parallel four is the same as par four?
No. OMP4, so the thing is, so OMP4 is like parallel four, except the join is called.
Parallel four except join. Oh, okay.
So
Join at the end.
yeah, so with a parallel four, you split it into parallel, and then when you get to the end of the loop, then you do a join. It's just built in.
Wait, I'm sorry, then that lost me. So the four has the join at the end, but what about the parallel four?
It has a join at the end.
Okay.
Parallel four has a join at the end.
Then what about the normal four?
Four is sequential. There's no need for a join. It's just
Okay. Okay. So,
I mean, if you just the point is you can say parallel four and then it will wrap the thing in threading logic and do a join for you at the end.
okay, then why does the OMP four exist?
So there are more complex things you can do, right? Like you want to have several parallel loops run, and you don't want to join between them. So you could say parallel by itself, and then you could say four on each of the loops. Well, so you could say parallel open curly, and then you could have OMP4 on each of the loops, and then a close curly, and I think that would run all the loops in parallel without a join. It's in case you want to do tricky stuff like that.
Okay. So
You-
primarily we should be concerned with parallel four.
Yes.
Okay.
I mean, the way most people use OpenMP, almost without exception, right, is people use only this instruction here. Reduction is the thing you should know, right? It's come up multiple times now. I mean, I don't know that you have to memorize the exact syntax for it, but you have to know what a reduction is. I would say you have to know OpenMP parallel four, and you have to know barrier and critical, what they are. I'm not sure what I'm going to ask about this because it's kind of a tricky thing to. Yeah, I think that's the kind of thing I'm likely to do.
Chapter 2. Do we have to know partial and total orders?
Is that by
Like the fact that they're like irreflexive, anti-symmetric.
Yeah, I probably won't ask. I don't think I'll ask you about that particular level of mathematical detail about that. I mean, the idea is just that, right? You have two tasks that can overlap. And if they overlap, it's kind of hard to say which one came first. That's all that's really getting to.
The difference between mutual exclusion, deadlock free, starvation free, lock free, and wait free.
Yes.
That's
So,
the next question.
all right. Can you answer it partially?
Yes.
Okay.
Like there are some kinds of true or false questions where I get confused.
All right. Well, let's start with blocking versus non-blocking. What does it mean for something to be blocking?
Blocking is like you can't go past that point.
Yeah. So if thread one dies, if thread one just stops doing anything, that if because of that thread two can't make any progress at all, then it's blocking. So if you want to think about it, if you get a lock, right? And then after you get the lock, you just die. Thread two or three or whatever can't do anything because they can't ever get that lock because it can never be unlocked because the thread that locked it went away, right? It's like, the only person with the key to the house locked the door and left town, right? So that's what blocking means. And that's why locks are blocking. But anything could be blocking in principle, right? You could have other code that could be blocking. You just have to ask yourself that question. You say, if this thread dies at an inopportune time, will it prevent anyone else from doing anything? And that tells you whether it's blocking or not. Now, if it's blocking, what are your possible progress conditions?
Deadlock free.
Yes. And starvation free. Those are the two blocking progress conditions. And the two non-blocking progress conditions are therefore weight free and lock free. Good. Okay, so weight free and lock free. Weight free means it will complete in a finite number of steps. That finite number could be 1,000,000, but it will always be that number or less, right? I can give you some definite number of steps, and it will complete in that many. Right. So if you have a while loop, I mean, depending on how you write that while loop might mean infinite number of instructions, right? So a typical example of that is you have, while compare and set fails, update old value, right? If you've got something of that nature, that can fail an arbitrary number of times, right? Depending on what the other threads are doing. And so that's lock free. But if any of those other threads stop messing with you, then you can make progress, right? So that's what lock free is. So a while loop, chances are that means you're lock free and not wait free if you're non-blocking. And then for starvation free and deadlock free, it's a question of, starvation free is kind of like the same thing that it's it says you can make progress eventually, right? So if you're doing Peterson locks, you have two threads and they're using a Peterson lock, you're going to make progress eventually. You're starvation free because you can't. If you both go for the lock at the same time and thread 2 gets it, then if thread 2 does its thing and releases and tries to get the lock again, it can't get it before thread 1, right? So thread 1 is guaranteed to make progress as things lock and unlock. So if you've got some kind of fair lock, then you're going to have starvation free. So that's the basic classification of things.
Okay, can we go over the 3 locks from this chapter? It's
Peterson,
filter, and bakery.
Peterson, filter, and bakery. Okay, so that's 2. Slide 46. 2. Okay, so Peterson, we have a flag and can protocol. First, we raise our flag. Then we either knock over our can or we stand our can up. We set our victim flag. And then we say, while the flag of the other thread is up and I am the victim. So if the flag of the other thread is not up, then I can proceed. If the flag is up and I am not the victim, I can proceed. And to unlock it, I just set my flag to false. I lower my flag. I say I'm not interested in the lock.
So which of the properties does this have?
Well, this is a lock. So is it blocking or not blocking? And can all threads make progress with a Peterson lock? Yes. So it's starvation. So if I have 2 threads and they're coordinating with a Peterson lock, they're going to be starvation free.
The deadlock free?
Well, I mean, in principle, well, yes. So if it's starvation free, it's automatically deadlock free. I mean, let me rephrase that. We would say it's not deadlock free because it is starvation free. We would go with the highest thing. So starvation free is higher, right? So we'd say it's starvation free, not deadlock free. It won't deadlock, but we want to call it by its best thing. It's like if you got an A in a course and I say it's a B because that it's at least a B. That's not really going to make you happy.
Same true. Block free, weight free.
Um,
Or you would say-
yeah, I would say it right. If it's a finite number of steps, I would say it's weight free. I wouldn't say it's lock free. I would pick one.
Your algorithm, it starts on 53.
So filter algorithm is just like, putting Peterson locks together in a way. So what I'm going to do with a filter lock is I'm going to have on each level, I'm going to have, I'm going to raise my flag to different heights, right? So my flag starts out, I raise it to level 1. I want to get into level 1, and I set the victim flag, the victim integer on level 1 to me. And then I do this thing, is there anybody else with flag at level 1 or higher? And if there isn't, then I get through. And if there is, I check the victim flag. And if I'm the victim, I don't get through. And so the way the filter lock works is at each level of the filter, one thread gets excluded. So if they all raise their flags to level 1, there's only one victim. So all of them, except that victim, get to the next level. And then on the next level, the same thing happens. It's like musical chairs. You keep losing chairs until there's one left, and that's the filter lock.
Is it fair?
It's gonna give you enough fairness that you can call it starvation free, right? You're gonna make progress through that lock. Because the next person who tries to get that lock and gets to your level is going to make themselves the victim, and then you'll get through. I mean, threads can overtake threads within the filter lock, so we don't usually call it fair, but it's going to make you starvation free.
What are the properties of bakery?
So bakery is a fair lock. And the idea behind bakery is that I have a doorway where I'm sort of getting my place in line, and then I will get in when my time comes up. So what I do is in the doorway, I find my place in line, which is the max of the labels of all the other threads, and I add 1 to that. And then while there exists somebody that has their flag raised, and while there is a label with a lower order than me, with a higher priority than me, I wait. And in this case, I break ties in the labeling order with my thread ID number, just to prevent things from getting stuck. So in some sense, this gives a little priority boost to the lower number threads because of that.
Do all locks provide mutual exclusion?
Yes, that's what they're for.
10% for sometime.
Yeah, but the semaphore isn't a lock, right?
Isn't it?
I wouldn't call it a lock. I would call it a semaphore. I've never heard a semaphore called a lock.
Slides say they're locks with city.
Yeah.
So a lock is really just like one and only. However, the semaphore can be thought of as a loose lock that measures how many.
Yeah, you could think of it that way. I guess in my head,
It's like,
I'm not sure. It may be that people define it different ways. In my mind, a semaphore is a different thing than a lock. It's
it's really kind of like a monitor. by monitoring stuff.
Oh, and you
So-
implement it as a monitor. Yes, you implement it as a monitor. And you use a lock to implement it. Yeah, there's potentially a semantic conundrum there. I'm not gonna like try to ask you true false is a semaphore a lock. In my mind, it isn't.
We know how to do pre and post conditions for sequential specifications.
Well, I mean, it's just like an assert statement, right? You just put assert statements before and after what you do. Um, there was this thing called aspect-oriented programming, which gained popularity for a while, and now I guess it's faded into non-existence. But the idea is you could say, like, before every method, verify that this is before and after every method, verify these things are true, and you could just sort of like say, here's a precondition for all methods that start with P or something like that. You could put these wild card specifications on everything. And that was gaining traction for a while, but then I don't know, people decided it wasn't working out.
It's still used in testing. We learned about that last semester.
Yeah, we did.
Did you?
We call it contract based.
Yeah.
Yes, so contract-based programming is a thing you can do, but having a language support for like doing the wild card, having language support for adding pre and post conditions to say all methods on a class.
More than just a return type.
Yeah. It was called aspect-oriented programming. And yes, doing contract stuff, that's something that you still do, but having this language support for this aspects thing, I don't think that's still done.
Doesn't sound familiar.
Yeah.
I feel like that would also waste like CPU cycles too, with constantly checking and starting.
So
Maybe it's how.
remember, no, I mean it is going to eat CPU cycles. It is if you do that kind of thing, and that's probably what killed it. But correctness is actually the most important thing.
Isn't that what tester?
Yeah. Well, but nothing guarantees it. But whatever. Yes. No, I don't. I'm not going to make a big fuss over histories. I'm more interested in. Linearizable, quiescent, sequential consistency, and consensus. Everybody's favorite topic.
We don't have to learn those like bubble tree things, right?
Bubble tree? Oh, you mean when they were proving? No, that was to sort of make you understand why it's the way it is. That was supposed to make sense.
This so confused me.
Yeah. Or it. I mean,
Look.
I'm sure it actually would make sense if I gave like a lot of time, but nah, that was just not feeling it that day.
Yeah.
Okay.
Things for precedence.
I'm sorry, what?
For precedence, do we need to know how to like reorder the stuff to make it?
I need a little more context. What are you talking about? Line 100
Slide.
of which deck?
So that I remember, but I'm not remembering which color is what.
Precedence. 103 you said, right? 100 and 101.
It's like rearrange it.
Yeah, no, I'm not gonna make you do those history things. As I say, the things I want you to focus on is the consistency conditions and consensus. See, this is another way to phrase those kinds of things, but it's kind of harder to understand. I guess that's it's kind of the realization I'm coming to. It's just the same way to do this, but it's harder to understand.
Same. I had atomic, and do we need to know anything about that? I think I just like skip that,
Example at the bottom about my atomic?
like the very bottom.
The bottom of what? You mean the last slide? Do you have a number?
The last one.
The last one. All right.
Like it's literally.
Okay, okay, I'm going. I'm gonna find this one.
Okay, up one more. Yeah, my atomic instant. Do we need to know that?
There is,
It's
Technically starts 150.
it's supposed to be just, atomic reference.
I don't know because there's no context on the slide.
I'm
before
pretty
it
sure it's
jumps
just
into it.
telling you what an atomic integer does, so like like. Read modify, right?
I think,
Okay, specifically, slide 154. Do we need to know that?
I think, correct me if I'm wrong, like, if it says atomic, it just means that one thing can access it at a time.
yeah.
It can be an int, it can be a whatever.
Okay, so yes, so I was just trying to show you, right? The idea here, right, is I can build this was an implementation of an atomic with locks. So I was trying to in this way it's kind of looking ahead to atomics, but phrasing it in terms of things I've presented up until then. Right? So you can implement the semantics of an atomic with locks. And you could and if you then subsequently use them, they would work just as well in terms of they would work almost as well in terms of progress conditions. I mean, it still could happen, right? That I get the lock and then right before I do the return, I die, right? So it's still blocking. But if you assume that that doesn't happen, right? Then if you assume that threads won't actually die like that, then you can use this and reason about it. It'll be composable, right? Because you won't get other locks inside. You're guaranteed of that. And so you don't get into those kinds of problems. And that's all I was trying to say. I was trying to implement the semantics of an atomic but show you how that looked with locks. You know, how you could get that semantics with locks, but the real thing is gonna be better.
Is another way of phrasing this as saying it's linearizable?
Yeah, it's linearizable, but I mean, the other thing I was looking for is composability. So instead of using generic locks, right, and just doing whatever you do with locks, you've got this one particular tool, right, which can do this one trick or few tricks.
It's technically not a lot, if you view this that way.
Yeah, it's right. So, I mean, you could think of it as not being a lock because it could be implemented without locks. But I shouldn't have said can be weight free. I should change that.
It's weight free if it's not a lot.
Yeah, it's weight free if it's not a lock. Yeah.
So OpenMP is shared.
Yes.
The other one is.
MPI is distributed.
So-
Well, how many computers do you have? Do you have one or do you have 10? Okay, then it's going to be shared memory. If you have 10 computers, then it's distributed because you want to run on all 10 at the same time. So if you look at what? So if you look at there's Frontier. Okay, this is the first machine to cross the exascale barrier. That's 10 to the 18th floating point operations per second. And if you look at the way this is built, right, they've got one computer with like 64 cores here, and one with here, and then one here, and then one here, and that's just this one cabinet. And then each cabinet has a bunch of computers in it. And then they have all these blue cables connecting them together at high speed. So this is the kind of machine you use MPI for. It's distributed. You start a process on all these different boxes inside this cabinet and across all these other cabinets at the same time and communicate.
Do we have to know anything about the origins of OpenMP or OpenMPI?
Well, OpenMP or MPI. No, I don't think you have to know the origins. You just have to know what they are. You should probably know a few things about MPI, like MPI send and receive, and I send and I receive.
What tells people to stop adding computers to the supercomputers so it's like done?
How much money do they have? That's what tells them.
We just had unlimited, like money and space, we could just build.
You can just keep building them bigger. But there's
Star.
there's a funny thing that happens. There's a funny thing that happens if you make the thing too physically big. There's this concept of latency, right? Which is the time it takes for a signal to get from one box to the next box. The bigger the machine you make, the more the latency is. Now, maybe at this scale you don't notice, but if you do something like grid computing where your nodes are scattered around the country, then the speed of light is actually a significant thing in your latency. Yes, Reagan.
Slide 10.
Of deck what? Oh, of OpenMP. Well, I don't know. Let's find out what slide 10 is. Yeah, this stuff, you should probably know that. I would make sure you understood shared private and first private.
I think there's a typo in first private. That's definition. They're initialized with the same veil. So
Veil, yes. They all come from the same veil. It's where the harpies live and yeah.
Was it taken from?
Value. Yes, it's value.
Why would you ever use like private over first private? Because first private you just get pre-initialization.
I would think that first private would be the default that you'd probably want, but if maybe the initial value isn't important to you, I'm not. I can't think of a use case right off the top of my head.
Do we need to know slide 5 on MPI?
It's like
Yeah, yeah. Just telling you how to run the thing.
Yeah, do we need to know that for the exam?
I mean, MPI exec minus N4. No, I'm not going to ask you that.
Slide 6.
Well, I mean, I'm not you haven't really seen much about communicators. The only communicator that I think you've ever really seen is MPI Com World. So I don't think there's anything there that this is in case you ever need such functionality. Is that this one?
Yep.
So you should know MPI send and receive, yes.
An alternative where I send and I receive. Right?
Yes.
And every I receive means an I wait, or just wait. Wait is the only one that exists. I wait doesn't exist.
Right.
Every I receive means a wait.
Yeah.
Okay.
I mean, you could wait on the sends if you wanted to, I guess. But I think it's normal to just wait on the receives. Yes.
The wait is kind of like join in the,
Yes, weight is kind of like join.
How about slide 10, collective communications, we need that.
I would know those three: broadcast, reduce, barrier. I mean, I'm not going to ask you to know all the arguments, but knowing what they are generally, I think is something you should know. Just, I wouldn't expect you to be able to write a program using MPI bcast from memory, but you should know what it is, what it does generally. I can't write a program using these things from memory. I have to go look it up. I mean,
Especially, well, for
for the first, well, I'm disappointed. We still have 2 minutes left.
I just don't think you're gonna ask us that.
I've always, every so often, Conway's game of life aggravates me because it can't have self-replicating organisms. And I just,
that out.
no, it can't. And I wonder what the minimum modification is to have a system that does allow that.
Wait, I thought they had the,
They have gliders and shooters.
but those are, okay, so you mean if the bullet itself created more bullets?
Yeah,
Okay.
Yeah.
Maybe a left bullet means it might need like.
I think they also have something where you have a structure and it peels itself away and disintegrates and then reforms over here, and then it peels away and reforms.
But it doesn't create copies.
It doesn't create copies. And it's so frustrating because if it only created copies, think how cool that would be. But it can't. And what is it that you need to create copies? What is the magic? And every so often I try to make some variant of Conway's Game of Life and see if I can make it make copies, and I've never succeeded.
Is there Wednesday 7 p.m. meeting?
I don't expect that there will be.
We're already having one, but will y'all be there?
We can look into it. What is it, Wednesday at CC's on campus or something? Highland Coffee. Yeah, I won't be there. I'm gonna be at choir practice.
We're also meeting our Thursday at 7.
On Thursday, I'm going to a Christmas party. Yes.
Like December 1st. We're not even through the first
People
week.
are. You saw the sororities and stuff.
Yeah, sororities make sense, it's still school year. Basically, like, after Friday, people start leaving.
Maybe it's a practice season.
I'm lucky people don't have Saturday finals this semester.
Wait, is